Moving on to our final characteristic of the NMR, we've talked about our number of signals, how many signals do we actually see, how many different non-equivalent hydrogens do we have in a molecule. We've talked about the chemical shift, where does it show up on the x-axis? We've also talked about integration, the area under the curve, or how many protons are represented in that signal. Now we want to be able to talk about multiplicity. This idea of splitting pattern is able to tell us an immense amount of information around the environment next door to our protons. So multiplicity is referring to the number of peaks that a signal is split into. So we could have a singlet when we just have one peak. A doublet is when we see a signal split with two peaks. A triplet is 3 peaks. A quartet is 4 peaks. Notice the symmetry as well with these peaks and how they look. A quintet would be 5. A sextet, 6. And a septet, 7. That's as far as we're going to go up. You can also call something a multiplet if it gets past, probably 5. A multiplet just means there's a bunch of stuff going on, a bunch of peaks. But notice how all of these, I just kind of want to look at this symmetry here where it goes up and down, up and down. And the middle peaks are always the tallest, right, on any one of these. And even with the doublet, they're even, right? The triplet, these sides are even, this is the tallest. I like to just represent that because that is true form of what we see for pure samples. If you don't see that, think something else could possibly be happening. Multiplicity arises from the actual magnetic effects that protons have on each other when they're neighboring. So we have these 2 carbons and we have HA and HB here, HA in red, HB in blue. Since the protons align with or against the external magnetic field, there could be 2 different types of relationships where HB is against the field or HB is with the field and HA is with the field or HB is without, things like that. There's options, right? And so with HA, what happens is HB will affect its peak. So multiplicity results from neighboring protons acting on each other. All right. Consider this example now where HA has 2 neighbors, 2 HB neighbors. So there's more options. Look at all these options. There's technically 3 possible environments, and these are the options. Think about coin tosses, right? And you don't need to know these environments, but what's important to be able to notice is that as we increase the number of neighbors, HA now has 3 neighbors. There are 4 possible environments. This is what we call the N+1 rule. When HA had 1 neighbor, it was split into 2 peaks. When HA had 2 neighbors, it was split into 3 peaks. When HA here in this example has 3 neighbors, it's split into 4 peaks. The N+1 rule says N is the number of neighbors, N+1 is the number of peaks that you see. So if HA has 3 neighbors, 3 + 1, HA's signal will be split into a quartet, 4 peaks. And that's what we are going to see with all of our protons and multiplicity. When does this splitting actually occur? It's not every single proton. Equivalent protons do not split each other. So if you have a CH2 group and those 2 protons are on the same carbon and they are identical, or if you had 2 CH2 groups that were in a symmetrical molecule and called them equivalent, that they would appear at the same position and be in the same signal, they resonate with each other. So they are equivalent and will not split each other. They don't count. To split each other, protons must be within 2 or 3 bonds. Non-equivalent geminal positions, if these were diastereotopic protons, they could split each other, or vicinal, right next door to each other. Next door neighbors, not down the block, all right? The neighbors that annoy you most are the ones that either live with you that are different or right next door to you, all right? If they are a couple houses down, they don't bug you. They don't interact with you that often, all right? So they have to be geminal or vicinal. There should not be another carbon in between those protons. These are just when we want to be able to look at which protons could possibly split. So the n+1 rule only applies to protons that are all equivalent, all right? So splitting patterns are observed for the protons that are shown below and can be more complex. So things like this proton right here has a proton here and it has a proton here. These two protons that I've drawn in that bluey green color are not chemically equivalent. We will not be discussing these protons and how they affect the red proton there because it's way too complex. We're just not going to deal with it. What we will deal with is a chemically equivalent neighbors. So here's a CH2 group, a methylene group. We have where it shows up on the integration or shows up on the chemical shift and it has an integration. We have 3 protons, 3 H's, and we have its signal right there as well. Now, what does this actually do? When we're looking at these two groups, they are adjacent to each other. So this isolated ethyl group, CH2, CH3, what happens? The 2 neighbors, I'll call these A, I'll call these B. The A signal has n+1 or 3 + 1 neighbors, which is 4 peaks. That's why we see 1, 2, 3, 4. For B over here, the 3 hydrogens, n+1, 2 neighbors, the blue guys. So that would be 3 peaks. 1, 2, 3. Beautiful. Now, what's really important to note here, simple splitting, notice the distance between these peaks is the same as the distance between the other set of peaks. This splitting pattern, not only do the peaks match up to the n+1 rule for being the correct number of neighbors, but the distance between those split peaks is also the same. This set distance is not the same as this distance. So these 2 signals are not neighboring each other. Very, very important. Their actual coupling constant, which is the J value, it goes in depth with the J value in the textbook. I'm not going to be talking about those values, but what's really important is this distance here is going to be consistent for neighbors. All right, so because these 2 distances are different, these are not neighbors. They might be on the same molecule, but they're not splitting each other. These guys, let's just zoom in here a little bit. This distance is the same as this distance. So these must be neighbors. Because not only does the n+1 values match up, but the coupling constants, the distance that that signal is split, is consistent. All right, some things that I just want to present that are really good to remember, really good to observe. And these are things that we'll see a lot of. If you see a singlet with 9 H's, all right, 9, that suggests the presence of a tert butyl group. Remember, right here, there is no hydrogen. So no neighbor there, meaning n+1, 0 + 1 is 1. That's the only time we get a singlet, when there's an adjacent carbon that has no neighbor. 3 CH3 groups add up to 9 protons, and those are chemically equivalent, all right? An isolated isopropyl group, right, has a carbon with 2 methyl groups and a single hydrogen. that hydrogen 6 plus 1 neighbors should have 7 peaks. 1, 2, 3, 4, 5, 6, 7. The 6 methyl hydrogens, right? The 2 CH3 groups add up to 6. One neighbor should be split into 2 peaks. Beautiful. Nice. Let's observe some splitting for ethanol. All right. So again, let's label how many hydrogens we expect. I'm going to make this a little bit bigger. Put in our hydrogens. We should expect to see 3 sets of signals. 1, 2, 3. Now, the OH proton, that's what I want to talk about first. 1 hydrogen there, right? We would expect it to show up somewhere between 2 and 5 ppm, typical for an OH proton. We'd expect the integration to be 1 hydrogen. And what happens with a proton bonded to a heteroatom, stuff like nitrogens, oxygens, sulfurs, is that they do not contribute to splitting and they do not get split. Think about that oxygen as a huge hedge that a neighbor has that does not want you to be seen or does not want to interact with you. Notice this 1 hydrogen peak right here, integration of 1 singlet appearing around 2.2. That is the OH peak. 2 hydrogens here, we would expect to see 2 H's, right? We know they're adjacent to an oxygen. So again, a methylene group, 1.2 ppm typically for the base. Add 2.5, we predict 3.7 ppm based off of our calculations, and that's what we see, 3.7. Nice. Now, it has, we're going to make it this right color, 1, 2, 3 neighbors. So 3 plus 1, I would expect a quartet. And that's what I see. Beautiful. Now, the methyl group starts at 0.9. It's beta to an oxygen. So it's 1/5 of 1 or 0.2 being added onto its shift. So that's a 1.1 ppm. Excellent. 1.2, that's fine. Close enough, right? Very, very close. Now here we have the 2 neighbors that we saw from the CH2 group. 1, 2 neighbor. So 2 plus 1 equals a triplet. Excellent. Now we can dissect not only how many sets of hydrogens do we see, how many signals, we know where they appear, their chemical shift, we know their integration values and assess how many protons are represented there from the computer data. We also can predict the splitting pattern. Now, the hydroxyl protein does not go into splitting. I said it acts as like a hedge. The reason for not undergoing the splitting is because of the rapid exchange of protons with trace amount of acid that could be in the solution, right? So because of that, those protons are switching back and forth. So the exchange of proton transfers that could be happening in the solution, happening in the NMR, blurs the shielding and de-shielding effects of neighboring protons. So sometimes we don't see that splitting occur. Using NMR for a aromatic compound, these 3 molecules might be difficult to distinguish by IR or mass spec. That should be an or mass spec, sorry. But what's great about NMR is that they are more easily distinguished because of the equivalent sets of protons, right? These 3 these two and these two, we would see 3 signals for this first guy when the methyls are right next to each other. If the methyls are 1, 2, 3 in their relationship, we see 4 signals. And if they're 1, 2, 3, 4 exactly opposite, we see 2 signals. All right, so there are ways to be able to determine more structurally sound things when looking at proton NMR. Best thing to be able to do here for wrapping up our proton NMR idea is when given a molecular formula and a proton NMR spectrum, which is what you typically will be given, 5-step process. Calculate the degrees of unsaturation like we've been doing from the beginning. Consider the number of signals and integration based off of what you see in this, the spectrum. Start analyzing things, start writing things down, right? Analyze each signal, draw fragments. Now, it doesn't mean that the molecule's splitting apart. It's not mass spec fragments. We're talking about if I see a carboxylic acid, if I see aromatic protons, start writing down different pieces of the puzzle. Then we can start completing and the structure by putting these pieces of the puzzle together based off of the neighboring multiplicity that we see. So it's really degrees of unsaturation followed by the number of signals and the integration and the chemical shift. Last thing that we want to do is identify multiplicity so that we can piece it all together. All right, we'll practice a lot more in class. I think the best way for this to be really understood is by practicing.